Well, this problem is going to involve work energy for sure, because there's a pendulum bob, and there's also a collision. It looks like we're going to have to split it up into 3 parts. There's going to be a work energy part, a collision, and then another work energy part. Let me get a diagram going here. So here's the pendulum at the lowest point of its motion. And let's see, we start off at a 33-degree angle. So this is L. This is 33 degrees. This little piece right here is L cosine 33. This little piece here is the height, which is L minus L cosine 33. Okay. Now this pendulum has a mass of ma, and then there's this collision, and then it rises up to some new height over here, where it's ma plus md. Right, and we want to find what is that second height, I guess. We'll call this h1, and this other height is h2. Okay, let's see. So h1, the height through which the mass falls initially, is 1.5 minus 1.5 cosine 33. So that's 0.24 meters. Okay, so it falls and then it's going to have a collision. So what we're going to do, part 1 of the motion is ma falls through this height h1. Okay, so during that time, what are the forces acting on mass A? Well, there's gravity, which points down, there's tension, and then off in this direction is the centrifugal force, which I didn't really leave myself room to draw. Sorry about that. And we have to use work energy, right? You can't use motion with constant acceleration because the acceleration is not constant. So we got 3 forces that could do work: normal force, centrifugal force, and gravity. Normal force does no work because everywhere perpendicular to the motion it points radially inward. The centrifugal force does no work because everywhere it points radially outward. Remember that when you're moving in a circle, okay, the motion is tangential, and the direction of the normal force or the centrifugal force is radial. And those are, by definition, at right angles everywhere, right? And so every point in the motion, the force, whether it's the normal force or the centrifugal force, is perpendicular to the displacement vector. Work done by gravity takes on the form of plus or minus mgh. In this case, it's mgh. It's positive because it moves down. All right, so now the work energy theorem tells me that if I sum the works done by all these forces, it's equal to the change in kinetic energy. Of course, this thing starts at rest, and so I'm left with the final velocity at the bottom of the motion is square root of 2gh1, which is 2.18 meters per second. Okay, so we're going to use that as the initial velocity for part 2. Part 2 is the collision. Okay, this collision takes a very small amount of time. During that time, the acceleration is not constant, so we can't use, F equals ma. Instead, we have to use momentum conservation. Now, we're told that the 2 masses stick together after the collision. So, let's see. Our momentum conservation tells us that the sum of the momenta before and after have to be the same. But we know that V2I(x) is equal to 0, that mass 2 is initially at rest. We also know that the masses move together after the collision, so we're going to simplify this to just read m1 v1I x is equal to m1 plus m2 vfx. Okay, so we've gone from basically 4 different velocities, 4 different unknowns. We've got one that's given, and two of them can be collapsed. So now we have an expression that only has two velocities in it. And we already know this one, v naught for part 2, that means v1ix, right? That is the initial x velocity for ball 1 when it's right here is 2.18, the instant before the collision. Okay, and the mass 1 is 250 grams, so we've got 0.250 times that initial speed of 2.18 is equal to the combined mass, which is 0.630 kilograms, times that final x velocity, and that works out to be Vf is 0.864 meters per second, which is the initial velocity for part 3. Now, for part 3, the two masses are going to rise up to their final height, h2 here. They have some initial speed here, v naught. At maximum height, of course, their final velocity will be 0. So again, we have to consider what are the forces that are doing work on the pendulum for part 3. So MA and MB move together, and they rise to height h2. So, okay, the normal force does no work in this part. The centrifugal force does no work. Gravity, in this case, does minus mgh2. I'm using the total mass now. Not that it matters, because it's going to cancel out, but and it's negative because it's moving up. And of course, h2 is what we're looking for. Yeah, so the work energy theorem tells me that I add up the works done by all the forces, and I set it equal to the change in kinetic energy. And of course, the final kinetic energy is 0 at maximum height. And then, so I'm left with just m total gh2 is 1/2 m total v naught squared. The m total cancels out, and I'm left with h2 is equal to v naught squared over 2g. That's 0.864 squared over 2 times 9.8, which is 0.038 meters. And we're just asked to find the maximum height above the lowest point in the motion. We're not asked to find the angle, so we're done.